Congratulations on your very first model. I'm sure it has performed really well. But actually judging the performance, or so to speak, the accuracy with which your model is predicting, is a field of contention. There could be a few ways you could think about trying to judge the accuracy, right? Imagine there is this targeting board here and you have two shots. I'm going to say, what's the average accuracy of the shots? One of the shots hits the target at minus 10 centimeters on the horizontal dimension. The other at plus 15 centimeters. So if I would say I just add them up and take the average of the error, what would happen is I have minus 10 plus 15 centimeters. So I'm ending with 5 centimeters divided by 2, and that's only 2.5. That's certainly not very telling about the errors we're seeing here. So we need to do something about these negative signs. Well, the initial idea, of course, might be I just ignore the negative sign. I just make this positive. So this is 10, and this error here is 15. That is an absolute error, and you would get a 12.5, which looks fair enough as a representative error of these two shots on the board. However, there is another way of doing it, which is taking the square. So I'm going to square 10, which is 100, plus 15 square. Then you get 162.5. If you divide it by 2, because you might have the average error, and then take the root, you get 12.7. This is pretty close to the absolute error, and it's kind of in the middle of these both errors as well. Why, however, would you want to use the square error? One of the reasons is if you use the absolute loss, right? What you really want to do is minimize that loss you have selected. And in the case of absolute, right, if it's negative, I just turn it around so that flips to the upper side of, and this here is just zero error. This just flips to the upper side. Where it's positive already, this remains. So you get kind of a kink as how costly it is to make an error for the model. On the other side, if you just take the square loss, you get a parabola, right? It's just a square function, nothing else, fairly standard. If you are incurring that kind of cost for making errors, then on the square loss, so-called L2 metric, it is much less costly to make small errors, but is much more costly to make very big errors. Whereas on the absolute loss, you start incurring pretty high cost for each error straight away. Even small errors give you pretty high cost. So with absolute loss, what tends to happen is you make the model much more parsimonious. That means you tend to try and eliminate full variables. Whereas with the square loss, you tend to take more information into account, but you really try and avoid to get it horribly wrong. So imagine one scenario, you're trying to build a stock market model. What you really want to avoid is predict something that leads to really bad loss in the end. You don't mind if the accuracy is not always that perfect, but you don't want to have, under no circumstance, you want to have that really big loss at any one day, right? So in such cases, the square loss tends to be a bit more suitable. It also has some other advantages from a mathematical side. We won't go inside that, but it is together with the gradient you see here, you can see it's just much easier to optimize on this function here. One more thing I would like you to be careful is when you're using these errors, and most of the time you will end up using the square errors, be really careful when you want to brag about the accuracy of your model. If your model on average makes an error in its prediction of 0.25, you might be tempted of just saying, my model gets it right 75%. 75% of the time, I'm able to predict if someone has died or survived on the Titanic. However, your true comparison is not that. Your true comparison is actually, in that case, flipping a random coin. Because if you knew nothing, you had no model, you would just claim all the time either alive or die, right? You just choose it random. In that case, you might get it wrong 50% of the time already. So your model, in fact, only improved by 50% upon the 50% random guess that you would have by standard.